Hello everyone. So in the we've seen in the last lecture we saw about we learned how to read the design into design compiler. We studied some coding techniques. We saw actually. So let's just spend a few minutes at this flowchart. So we have seen libraries a couple of lectures back. We saw what link, target, and synthetic library means. In the last lecture, we saw how to read the verilog into design compiler. We saw how to code RTL for synthesis. Now, in this lecture, we look at how to define the design environment. Before we come to the most important part of setting the design constraint, we should see how the environment is designed, in what environment we synthesize the design. So this presentation is divided into two parts. The first part we will see how to partition our design or synthesis, what are the partitioning guidelines, and in the second part we will see the how to define what is meant by design environment and how do we set the design environment. Let's first look at the few terminologies specific to design compiler, or I would say now they are common to all the EDA tools. We'll see what these terminologies are and how they are used inside the tool. So first let's look at design. What do we mean by design in the context of an EDA tool like synthesis design, like Synopsys design compiler? So designs are circuit descriptions that perform logical functions. So for example, you're designing an 8-bit CPU. So that is a design for synthesis. That is a design for simulation and so on. So designs are described in various formats such as VHDL or Verilog. Logic level designs are represented as sets of Boolean equations. Gate level design. So a design, let's say an 8-bit CPU, an 8-bit microprocessor, it can be represented in a Verilog SDL. After synthesis, we'll get the gate level netlist. So it can also be represented in netlist format as part of as interconnected cells. So a design is a CPU, but the representation depends on your usage. If you want to use it for RTL simulation, you have to use the Verilog design. If you want to use it for timing analysis, you have to use the netlist format. Designs can exist and be compiled independently of one another, or they can be subdesigned in a larger design. By that definition, designs are either flat or hierarchical. Flat designs do not contain any subdesign. They have only one structural level. However, they may contain library cells. For example, a simple design like a full adder or a half adder will contain a list of library cells if it's a netlist. For example, it will contain AND gate or gate, but inside it does not contain any other design. So that is a flat design. On the other hand, all complex designs are more or less hierarchical in nature. They contain one or more designs or subdesigns. Each subdesign can further contain subdesigns. So it is a kind of a design hierarchy at different levels. Usually RTL is in that format. Although netlist can be flat or can be hierarchical, we will see many examples during this course. Now let's come to design objects. So here's one example. So there's a design called top, which has ports A, B, input ports A, B, C, D, and clock. Output ports out, which is a bus, 2-bit bus. So when we talk in terms of synthesis, this top level description is called a design. The ports, the input output ports are simply called ports, but the ports of the designs which are instantiated inside the top level design are called pins. So the difference between pin and port is that ports are pins of the top level and all the ports of sub-designs are called pins. So please be very clear about the difference between ports and pins. Ports are always, when we talk about, when we say something is a port, We mean either it's an input or an output at the top level. A pin is usually pin is associated with something which is inside the top level, not at the boundary. So here there are two subdesigns contains two subdesigns which we can also call reference, encoder and reg file. U1 is an instance of encoder, U4 is an instance of reg file, U2 is an instance of INV, U3 again is an instance of INV. So designs are top, encoder and reg file. Please note we are not calling an inverter a design. Why? Because we differentiate between design. By design means say either a combination of cells or an RTL design. Inverter here is a standard cell component. References are again encoder reg file. So now inverter here, although inverter is not called a design, it can be a reference. We'll see the difference between reference and design. Usually when you talk about other tools apart from design compiler, you will not hear term like reference. It's always design that is being used. Again, instances are the instantiations of any design or reference. So these are the more descriptive definitions. So a design consists of instance, nets, ports and pins. It can contain sub-designs and library cells. Most important thing, the active design. The design that you are working on inside design compiler is called the parent design. In fact, this is also a command. Parent design is also a command. So you want to set some design which you want to work on, you can use the parent design command. Most of the commands, let's say you want to query what all ports are there in the design. So most of such commands will work on the current design. They operate within the context of the current design. Reference is a library component or a design. Again, see, reference is a library component or a design. So reference can also be used for a design that can be used as an element in building larger circuits. It can be a simple logic gate or a more complex design. One design can contain multiple occurrences of the reference, and each occurrence is called an instance. The idea of reference is that it lets you optimize every cell in a single design without affecting the other design. This is a unique feature. That means, for example, see this design. Although the reference inverter is same in both the cases, but the instances U2 and U3 are different. The loading on U2 and U3 will be different. The inputs driving U2 and U3 are different. So the design compiler will optimize U2 and U3 differently based on their own input and output conditions. This is what it means here. Instance or cell is an occurrence of a reference, occurrence in a circuit of a reference. Each instance should be a unique name. A design obviously can contain multiple instances, like we saw 2 instances of inverter. Each instance points to the same reference but has a unique name to distinguish it. You can also call it a cell. So a cell, a design, an instance which is not hierarchical is called a leaf cell. For example, in this one, encoder would be more or less a complex circuit. It will contain few logic gates. Similarly, reg file will have some clocks. So encoder and reg file are hierarchical design. They are sub designs, but they are hierarchical in nature. On the other hand, INV is not hierarchical. There is no other hierarchy inside inverter. That's why we call it a leaf cell. A leaf, the corollary is from a tree, where a tree contains branches, branches contain leaves. Leaf is the last non-hierarchical unit. That's why it's called a leaf cell. There's also a command called current instance. A unique instance of a library cell is called a leaf cell. Some commands will work within the context of hierarchical instance of the current design. Ports are inputs and outputs of a design. They can be input, output, or in-out. Pins are inputs and outputs of cells within a design. So nets are wires that connect ports to pins and pins to each other. So here For example, this can be a wire which connects code to this design. This Q0 to INV input is a wire, again INV output to T0 is a wire, and so on. So please be very clear. If you are confused, then read more about it. Mostly people are confused between port and pin. Just read these descriptions here, and maybe you can read more on the design compiler manual. So this example tells what is the difference between reference and a design, or it clarifies other. So here the XREF is a design. It contains two references, man2 and multiplier. So the designs that are loaded inside design compiler are man2 and multiplier. Here U1, U2 and U3 are instances of man2 and U4 is an instance of multiplier. So man2 is instantiated 3 times, multiplier instantiated once. So the references of man2 and multiplier in the XREF design are independent of same references in another design. That means if you have another design which again has a reference man2, this reference would be different from that reference. And plus, if you go down further, this instance, although in terms of functionality, at RTL level it is same as U1 is same as U2 in terms of functionality, but when it goes to backend, the boundary conditions of U1, U2 and U3 are different from each other. So they will be optimized differently. Now let's talk about a very important concept called partitioning for synthesis. What does partitioning mean? Partitioning means dividing your design according to different design goals such that it aids synthesis and in turn it aids performance in area. So the metric here can be that, let's say some design is taking a big complex design is taking a lot of time in synthesis. What you could do is you could partition it into smaller designs and synthesize them separately to save on runtime. Thus, it might also help you in terms of performance and everything. So, by partitioning a design effectively can enhance the synthesis results. It can reduce the compile time. Compile time here means the synthesis time, and simplify the constraint and script time. Partitioning affects block sizes. Although design compiler has no inherent block size limit, but obviously as we keep on increasing the complexity in RTL, the compile time will keep on increasing. So there are again two extremes. If we make the blocks too small, if we make too many modules, then we are actually stopping design compiler from utilizing we are creating artificial boundaries that will restrict effective optimization. Again, on the other hand, if we make very large block sizes and keep everything inside one module, the runtimes will be more. So these are following important points which can be kept in mind for partitioning. Partitioning for design reuse, keeping related combination logic together, and so on. We'll see them one by one. Let's look at the first one, partitioning for design reuse. Now, what does design reuse mean? Design reuse means that, let's say, I'm making a circuit called a full adder. Now, I know that a full adder is a very generic circuit. A lot of designs can use this. So I should be very careful in designing such blocks that can be reused from one design to another design, one project to another project, one application to another application. So design reuse decreases time to market by reducing the design integration and testing effort. So we should partition it carefully such that such designs are easy to reuse. In fact, the whole industry is right now design reuse is a very important concept now, and chip teams usually pick up designs from different teams, just hook them up, and they can come out with a chip for, let's say, mobile phone or a TV very quickly in a matter of let's say 3 or 4 months. So this is enabled by design reuse. So the important points are that for such designs we should thoroughly define and document the design interface. We should try and use the standardized interfaces wherever possible. The SDL code should be parameterized depending on, let's say you are making a generic 8-bit microprocessor. So you should let's say you should make something parametric. For example, you could make the number of generic registers to be parametric. You could give the flexibility to the user to have, let's say, 8 generic registers or 10 generic registers, depending on the application you're using it for. So SDN code should be parameterized. So this is when it comes to the planning of the design. When you're designing something, you should first analyze whether it can be used by a different project or a different tip, and then design it accordingly. Second very important thing, which is applicable for at a lot of levels, is keeping related combination logic together. Now, by default, design compiler cannot move logic across hierarchical boundaries. So hierarchical boundaries, I mean across Verilog modules. If we talk about Verilog, therefore it is very important to keep related combination logic together. If the related combination logic is together, then design compiler can use all its algorithms to optimize the design. So for best results, there are two strategies. First is grouping related combination logic and its destination registers together. So when working with the complete combination path, therefore design compiler has the flexibility to merge logic, resulting in a smaller and faster design. It also simplifies timing constraints. We'll see how, and it enables sequential optimization. We'll see as we progress in this course. We'll see how do we define the timing constraint and how does keeping combination logic together with sequential counterpart will help in making the job easier. Second thing is eliminate glue logic. Glue logic is the combination logic that connects blocks. For example, you have a structural design. We saw an example in the last lecture where you have an accumulator where you have an adder and a register bank. Now we should try and avoid glue logic at the top level. So the top level will simply connect the designs together. And if we have glue logic at the top level, we again have boundaries, we have subdesign. The design compiler will not optimize the glue logic effectively. Instead, we should move this logic into one of the blocks, either the source block or the target block. Now this gives flexibility again to design compiler to optimize that. So now let's look at this figure. So you have these three boundaries, three designs. The dotted line here tells us what are the module definitions. Now see, this is a critical path. Critical path means it is highly critical. That is, this is the path that has maximum delay. So there is a big combination cloud. Again, there is a big combination cloud. Now here, design compiler can optimize within this and within this. But again, same thing. It can optimize either within this or within this. Now, if we make this into one boundary, we combine all these together, then design compiler can optimize all these three combination clouds together, and it definitely gives it more flexibility. This is a very important concept of registering block outputs. This helps in simplifying the timing constraints. It's a very important thing to make sure that all the outputs of your design come out of a register, and there should be minimal or no combination logic between the register and the output. We'll see how does this make our job easier when we write the constraint. The drive strength on the inputs to an individual block always equals the drive strength of the average input drive. We will see the importance of this statement later. Just keep this in mind for now. So for example, if we are defining input delay, if we are defining input timing constraints here, if there is a combination logic between this register and this output, then it makes a job happen. Therefore, we should make sure that there is no or minimal combination logic between output and the register drive. So this is the output and this is the register, and there is minimal or no combination logic between these two components. When we study set input delay commands and set output delay commands, then we understand that this makes the job of defining these delays very much easier. So there are a few tools out there which actually read in your RTL. It will tell that you have these and these problems before even going to synthesis. One such tool is Spyglass. So when you actually read in your design in Spyglass, Spyglass will actually tell you whether all your outputs are registered or not. Next, part testing by design goal. Now let's say you have one example is that you have a design, a part of the design, which is very time critical, very much time critical, and there is some other part of the design where you are very much concerned about the area. Now, since these two have different and competing goals, it is better to keep them in different hierarchies. Such that on one of the design you can focus on the timing part, and other design you can focus on the area part. So one example here is so the idea is to isolate the non-critical speed constraint from the critical speed constraint logic. We'll see in advanced synthesis concept how can we actually take a small part of the design and tell DC to work more on it in terms of area and in terms of power. So one was the earlier one was a design goal. Now this was a compile technique. Now when you look at the compile command, the command that actually performs the optimization, it has a lot of options available. One such option is enables it to actually use multiple stages in the design as opposed to flattening the design. So when we increase the number of stages, we are increasing decreasing the area but increasing the performance. When we flatten the design a lot, we are increasing the performance and reducing the area. So these are again two competing goals. So one example is that highly structured logic such as array detection circuitry, which uses lot of XORs, is better suited to structuring, but random logic is better suited to flattening. So since these two are different type of goals, these type of design should be kept separately in separate hierarchies. Other guideline is keeping shareable resources together. So design compiler is actually pretty good at sharing resources such as adders or multipliers, but resource sharing can only occur if the resources belong to the same Verilog always block. Although even if they belong to different always blocks, you can tell design compiler to actually do resource sharing, but that's again a separate set of commands. So to make design compiler work out of the box for you, it is best to actually do the resource sharing in the RTL itself by including them in the same always block. Now here's our example of coding. In the first part of the code, A plus B is going to one pin of the mux, C plus B is going to another pin of the mux. The CTL selects which goes to the register input, either A plus B or C plus B. See the second example. Now in this, the RTL is arranged in such a manner that the mux here is moved ahead, so that it selects the CTL selects between either A and C or B and D, and then there is only one adder. Obviously, the second instance is a better RTL design, such that the resource sharing is done right at the RTL level. So that is, even if we code we code as given in the example 1 here, in case of unshared resources, if these A, B, C, and D, if these two additions are done in the same always block, then design compiler will give you this kind of a message. It will know that it can share resources, so that it will move the mux ahead and replace these two adders by a single one. Keeping user defined resources with the logic grid right. Now there can be a few complex blocks in your design which are user defined functions, procedures, or macro cells. Now whenever there are such cases, and obviously design compiler will not automatically create multiple instances of these. since it doesn't understand the complexity, it doesn't let design. If the function is not simple, for example, there is a very special memory. Now this special memory can never be inferred; it can only be instantiated. So it should be the part of your RTO itself, the instance. Now design compiler will not create multiple instances of this to resolve any timing problem or any loading problem. So what we should do is that we should keep these resources together with the logic they write, such that later if we find that, let's say you have one user defined resource here and it drives let's say a net called parity error that is a fan out of, that has a large fan out, let's say fan out of 10. Now if we keep this in the same hierarchy and if we later realize that this complex resource is not able to drive such a load, we could create multiple instances easily and split the load. This is again a slightly more complex example. It is not you will not come across this problem very early in the design flow, or when you are doing the simple RTL coding while learning the process of synthesis. This is a more advanced problem since it involves some complex resources like special memory or mapping. Again, isolating special function, this is more applicable for bigger designs or even at the chip level, where you would want to separate your clause initial logic, your pads, your boundary scan, any asynchronous logic. So all these different types of logic should be in separate hierarchies. So this is how a chip is made. Usually a chip will have a top level that has separate pads, a clause initial logic will be a separate module, boundary scan will be a separate module, any asynchronous logic will be a separate module. Again, core logic would be divided into different functions. There might be a CPU, a video processing unit, a peripheral unit, and so on. So that was all about design partitioning. Till now, this concept was only theoretical, but when you start coding, you would start appreciating the value of each of those principles later in the flow. So if you miss, let's say if you do not register your output, you will find at the later stage that you are having problems in defining timing constraints. And then you will go back and probably register the output. So it's good to know these concepts beforehand so that you can actually use them in practice. Now let's look at the optimization priority. As stressed the fact earlier that design goals often conflict. For example, area, timing, and power. They are conflicting design goals. The optimization engine of design compiler must resolve conflict, and therefore the priority comes into picture. So DC design compiler priority is first it will focus on fixing DRC. Only when it fixes DRC, it knows that it's the timing. It can believe in the timing. So DRC is always number one. Next comes the timing. Obviously, the design should meet performance even if it has a slightly more power or area. Then comes the power, and last comes the area. This is the default priority. These priorities can be modified with set cost priority, but it's not a very popular choice because this priority is very logical in nature. How this is based on the facts of how designers perceive how designers want their design to be. One example: any processor that works for a handheld device, obviously DRC has to be meeting first. All the design rules should be met before we can talk about timing. Then the most important factor for a processor chip is the speed. So if you're targeting a 1 GHz processor, it should meet 1 GHz, and therefore it should meet timing at 1 GHz. Now, since it's a handheld device like a mobile, power becomes very important. So it's a battery operated device. So next comes power. Obviously, area is also very important because it should be smaller in area, but area is secondary when compared to power and timing. So I have not seen many people playing with set cost priority. but it's good to know that this priority can be changed, can be modified. Now, before talking about timing, so on the previous slide we saw that design compiler will first fix BRCs and then go on to fix timing. So, what are the factors that affect timing? Constraints that we describe as delays available from register to register, input to register, register to output, and so on. We'll see a lot more of this in the next lecture. But more important is, the first important thing is the conditions under which the delays are calculated are not described by these constraints. For example, when you define a clock or you define an input delay or an output delay, these do not talk about the sufficient and necessary conditions under which delay calculation would be reliable, because all the delays depend on all the delays of the design depend on the capacitance. For example, the delay of a gate depends on the capacitance the gate sees on its output. That capacitance will be comprised of the inherent gate capacitance plus the net capacitance plus the final capacitance. Plus, it also depends on the input transition time. It depends on what is the voltage, what is the temperature, what is the process we are talking about, and so on. So now in this lecture we are focusing on the second thing. We are focusing on the environment conditions. This is what I mean by the environment conditions. So we look at all these things. We look at how to provide the input constraints, input environment conditions. We'll see how to set the operating conditions. We'll see how to, since synthesis, at the synthesis level we don't have the information about the nets since the design is not routed, not yet placed and routed. We'll see how to estimate the wire, the interconnect data. We'll see the output loading conditions, how to set them. This is called all these conditions combined together, that is the operating conditions, the interconnect data, the input boundary conditions and output boundary conditions combined together is called the design environment. So we look at the 4 cases of how to specify input transition, how to specify output loading, how to set the PVT condition, how to set the parasitic action. Let's first look at the this part, the operating conditions. So the operating conditions, I've also gone through this earlier. Let me just quickly go through it again. The operating conditions include the following parameters: process, voltage, and temperature. These are not fixed values. These are everything is a range. For example, process is again a range from slow to fast. Voltage is again a range, which is typically minus 10% of a target VDD to plus 10% of the target VDD. Temperature is again a range. It could be from 0 degrees C to 125 C. So the chip is intended to operate in all such ranges and in all the possible combinations. So the process variation is it accounts for the deviations in the semiconductor fabrication process. Not every transistor, not every PMOS, not every PMOS, not every NMOS on that chip. There are now billions of PMOS and NMOS on a chip, and not every one is expected to behave in a similar manner. Some will be faster, some will be slow. So this physical effect is modeled by the process variation. Usually it is treated as a percentage variation in the performance calculation. So you could say that one way of modeling it you could say that let's say the typical speed of the inverter, let's say the typical delay of inverter is X. So the worst case delay will be 20% more. So the worst case delay would be 1.2. Although this is a very simplistic model, and the present day models are much more complex. Supply voltage variation, it can vary from the ideal value during day-to-day operation. It models that physical effect. Often a complex calculation using a shift in threshold voltage is employed, but again a simplistic model would be to make sure that the chip works at minus 10% of VDD, for example. Temperature variation is unavoidable in every day operation of a design. Each part, not all parts of the chip will have same temperature. And for example, you're using a mobile phone. If you talk for half an hour, the temperature will keep on increasing. The temperature of the chip. If you keep your phone on standby, the temperature will decrease. So the temperature depends on the usage mode. Plus, different again. In a mobile phone, the CPU, the processor chip, the processor part keeps on working all the time. So it will get a higher temperature reading compared to the video decoder part, because video decoder part will only work when you are watching a video. So this physical effect is modeled using temperature variation. So it could again be a linear model or a much more complex model. So the idea is that for synthesis, since synthesis is the idea is to optimize the design for maximum performance. So we should choose the corner in such a way that it is the worst conditions for the operation of the chip. So when we talk about operating condition, we should synthesize it at a slow corner, because now at a slow process corner, the delays will be more. So it will be a limiting factor in terms of performance. Again, we should choose a higher temperature in most of the technologies. I say most because some technologies have a negative temperature effect, where when the temperature is less, the delays are more. So but let's not worry about that. In most of the technologies, higher temperature means higher delay. So we should choose a higher temperature. Again, we should choose a lower voltage. Why? Because lower voltage means slower devices. So typically, almost always you would choose slow corner, high temperature, and low voltage. If your design is optimized and meets the performance criteria in this corner, it will meet the performance criteria in any corner. So most logic libraries, so when you start a synthesis, you will see that the Synopsys 90 nanometer generic library will have predefined set of operating conditions. So how to know what operating conditions are? First, we should have the library read inside design compiler. So if you want to just see what operating conditions are there, you can follow the examples. You can say read lib, read file, and you can read the DB. Then you can type a command called report lib. Report lib will tell you, it will give you a report in this format. It will tell you what all operating conditions are available. It will tell you the process factor. This is the factor that is multiplied by the delay part. It will tell you the temperature and the voltage. It will tell you what is the interconnect model. We will come to that later. Again, if your library is already loaded, you can use a command called list libs. It will tell you what all libraries are there. Then you can again do a report lib on that particular library. So now the command to set operating condition is this: set operating conditions. WCCOM here is the operating condition name that is included in the library, and you tell a design compiler what library is this operating condition in. This is the way you set operating conditions. Again, the key thing here is to remember that you always choose the worst case corner, worst case delay corner for synthesis. Next comes the interconnect part. Now at synthesis level, we do not have any knowledge. There is no accurate interconnect data. Anything has to be an estimate. So one model to estimate interconnect is called a Y-load model. It's a very popular model. Y-load model is the simplest method of estimation. So that we call it WLN. WLN gets a rough value of the total wire cap based on the size of the chip and the fan out of the net. So for each net, now this data, this WLN, so what DC will do is for each net, it will go to this WLN and see what this net, so there will be different Y-load models. So it will see that, okay, for a particular fan out, it will go to that listing. So that listing will contain, it will tell you the typical value of the capacitance for different values of fan out. For example, if the fan out was of 10, it will tell what the cap is, what the typical cap. The design compiler will pick up that cap value from there. It is not accurate, it is just an estimate. So for each net, Y-load model obtains two values, a resistance value and a capacitance value. WLMs are not specific to each design and based on statistical averages. So what happens in the industry is typically that, let's say we choose a particular technology and we'll choose the standard cell library vendor. That vendor, based on the history of the devices, will give a set of WLMs for that particular technology. And the WLM for one technology will be different than WLM for other technology, because the resistance and capacitance value, they change from technology to technology. So now, one is what Y-load model to choose. Second is what is the mode. So design compiler supports three modes for determining which Y-load model to use for nets that cross hierarchical boundaries. Now, in most of the cases, your design will have hierarchy. So design compiler has three WLM modes. One is the top. In this case, for each net, DC will simply use the Y-load model that is used by the top level of the design. The tool ignores any Y-load models set on the lower designs with the set Y-load model command. You can use the stop mode if you are planning to flatten the design. If you are planning that the complete design, all the hierarchies will be removed after synthesis, then we can use this. Obviously, this is the most crude form of Y-load mode. Second is enclosed. So now DC will look at the net and it will look for the design that completely encloses this net completely, and it will use the Y-load model for that design. You can use enclosed if the design has similar logical and physical hierarchy. Third is segmented. This is the most accurate estimate, I would say. So it will divide the net into segments, and for each segment use the Y-load mode for the design that contains this net. Let's look at the figure to understand this better. Now we are talking about this net. So let's say there are three Y-load modes available, 3 or 4 Y-load modes available to us: 50 cross 50, 40 cross 50, 40, 20 cross 20, 30 cross 30. Each of these Y-load modes, as the name suggests, depends on the area. So the most popular implementation is that you have different Y-load models for different areas. So let's say your chip area is 20 cross 20, you will use a Y-load model based on a 20 cross 20. 50 cross 50 Y-load model will have more resistance and more capacitance compared to a 20 cross 20 Y-load model. Now, when we talk about this net, if we set the Y-load mode to be top, DC will still choose a 50 cross 50 model for this net, since we said it's top. For any net in the design, it will not choose 20 cross 20, 30 cross 30 or 40 cross 30. Obviously, this is more pessimistic in nature and it is very simple in nature as the implementation goes. When we go to enclosed, we go to slightly more accurate implementation. It will look for the smallest design that encloses this net. 20 cross 20 does not enclose this net completely. 30 cross 30 also does not. 40 cross 40 encloses this net completely. So these are three segments: 1, 2, and 3. So it will choose the Y-load mode to be, or Y-load model to be 40 cross 40 if the mode is enclosed. Again, for the segmented one, it will choose 20 cross 20 for this segment of the net. For this segment, it will choose 40 cross 40 for this segment and 30 cross 30 for this segment. So first, you choose what is the Y-load model. Usually it will be area based or fan out based, however. And second, you choose the mode. So most logic libraries have predefined Y-load models. You can open up your 90 nanometer CMOS generate library and verify this. You can use reportlib. Reportlib will also tell what is the Y-load model. The report will be something like this, the one given on the right hand side. It will tell what all Y-load models are available. It will tell, for example, here 05 cross 05 is one Y-load model. It has some values of R, C, and flow. It tells for what fan out what is the length. Also, it gives automatic selection of biload model based on area. This is one nice feature in the biload model, where you could specify the max area and tell the tool that for a block which is up to this area, use this biload model. Between this and this, use this biload model. So there will be different biload models here, and the tool can choose based on the area. For hierarchical design, what biload model will it apply? Depends on the mode, which is either top, enclosed, or segmented. This slide here tells about what are the commands. So the default biload model library attribute defines the default biload model for the library. As you saw an example, some libraries support automatic area-based biload selection. So it uses that feature and it will select a biload model based on the total cell area. We can turn this off, auto biload selection, if you want to specify the biload ourselves. Since automatic biload selection can increase the runtime. Since for let's say your design has a lot of hierarchies, many of these hierarchies will be small, so it will pick up small biload model. Again, for larger blocks, it will pick larger area-based biload models. So it has not many different kinds of biload models for different parts of the design. This can increase in runtime. If you want to set this off, you can use this variable. The library can also define a default biload mode. If the mode is not defined, design compiler will choose the mode top. So these two commands, set biload model and set biload mode, these two can be used to select these explicitly. You can say what biload model to use and what biload mode to use. So the biload model we choose for a design depends on how the design is implemented. So it is best to look at the technology library supplied by the semiconductor vendor to determine the best biload model. The report design and report timing commands can be used to see what is the biload model used. We will see more of these commands later in the lecture. To remove the biload model, we can use this command, report biload model, remove biload model. Now, all the commands I am discussing in these lectures, please go back to your example design, whatever you are synthesizing during your experiment, and use these commands to verify that use the command reportly, for example, to verify that your standard cell library indeed contains some biload models. Use these commands, set biload model, set biload mode, do a lot of experiments till you are comfortable with the control. So these are the assignments for any command I discuss. Please go back, see the help, see the man page, experiment with it to learn about it more. So we saw the operating condition part, which defines the PVC of the design. We saw how to estimate the interconnect data. Now the two things remaining are the input boundary and the output boundary. So let's look at the input boundary first. So the most important thing regarding input boundary is that we should model something called the input transition. So for modeling input transition, there are two ways. One is that we tell DC that each of my input has some transition, some positive transition. If we do not specify this, the DC will assume the transition to be 0, and it is wrong. It is optimistic, because your design will be driven by some cell, and the transition will never be 0. It will be greater than 0 for all the practical cases. So, or the second case, we can choose. We can tell design compiler that I am expecting my input to be driven by this cell. In that case, DC will use the timing characteristics of this cell. So even if the input transition here is 0, there will be some transition here. There will be some transition at the input. Why? Because we told DC that there is a driving cell here. What is the effect? Rise and fall transitions on the input port affect the cell delay of the gates. So transitions here will affect the delay calculation of the combination logic here. Therefore, it is very important to accurately model transition times on all inputs. How do we do that? Two very famous commands. By default, DC will assume 0 drive resistance on input ports. means infinite drive strength. Drive resistance, so the term drive strength is reciprocal of drive resistance. So zero drive resistance means infinite drive strength. That means that port can drive any gap or any resistance, which is not obviously practical. To set realistic drive strength, we use one of the following commands: set driving cell or set input function. We use the set driving cell command to specify the drive characteristic. Now we have to tell, for example, when we use this set driving cell command, we tell DC that I am expecting this input, let's say, to be driven by a buffer port from this library. So DC, so this command is compatible with all delay models, including NNDM and piecewise linear delay model. So this command associates the library pin with an input port so that the delay calculators can accurately model the drive compatibility of an external driver. What we did here is that we told DC that this particular type of cell, for example, a buffer port drives my input. Now DC will use the characteristics of this cell to calculate a reasonable transition time of the input. Or if we do not know, if we cannot estimate what kind of cell will drive your input, you directly give a value, some value at set input function. What will that value be? We'll see. Now we see the output boundary. So the capacitive load on the output port affects the transition time. Obviously, if you assume the load to be 0 here, it is not realistic, and it will affect the optimization in this part. So the cell delay, for example, this clock is driving, the Q is driving the output directly, output A directly, and we assume a 0 load at A. This can affect the optimization of this cell, this sequential cell, since the boundary conditions are not accurately defined. How do we model this? We model this using a set load command. Directly we tell DC that my output out drives, for example, a cap of 20 femtofarad. So this is the command: set load, the cap value, the units will again come from the library, and the output port. By default, if you don't do this, it will assume 0 capacitive load, and it is not correct. It is not accurate. So this, how does the cell, for example, you have this sequential cell, you have, let's say, 3 different type of drive strength in your library: X1, X2, and X2. Based on the load here, if the load is 0 here, and you don't specify set load, DC will assume a 0 load. It will use an X1 clock, X1 drive strength clock. However, let's say when you go to backend or somebody else uses your design and he connects, let's say, 4 inverters here. Now this X1 will not help. The transition will be very, very bad because it will not be able to drive this much load. So it is good to estimate that and apply that estimated value as set load, so that DC, what it will do now, it will maybe upsize it to either X2 or X4. This will enable the guy who is using your design, will see good transition numbers coming out of a design. Right? Now the question is that I have my design, I do not know what happens at the input boundary or the output boundary. I am not aware of them. I do not know in what conditions my design will be used. Conditions mean input and output boundary conditions, not the operating conditions. I know the operating conditions. Operating conditions are more or less specific, but I do not know what kind of cells will drive my input. I do not know what kind of fan out my output will drive. How do we estimate in such cases? Estimation is called load budgeting. This estimation is called load budgeting. So how do we create a load budget? At the inputs, we assume that there will be a lead driver. Why? Because this is the worst case. We should be prepared for the worst case scenario. So you could assume that a buffer of the lowest strength or an inverter of the lowest strength is driving my input, and you can set driving cell accordingly, or if you do not want to set a driving cell, you can apply the transition number. Now, what transition number you would apply? You would apply. Remember the lookup table we saw in the library page? There, a buffer, for example, an X1 buffer has a maximum level of transition. You could apply that maximum transition at the input. So that will be the worst case transition for this input. So assume a weak cell driving the inputs to be conservative, or set a high value, the maximum value of the input of the transition from the lookup table of a lab. Limit the input capacitance of input port. Ideally, I would say that if you have done the job well in the first case, the second is not entirely needed. This is very important. Estimate the number of other major blocks the output may have to drive. So the output estimate. If you cannot estimate, then what you do? You apply a load here, which is typically the maximum load your combination cell here can drive. So for example, you have 3 clocks, X1, X2, X4. Choose what maximum load your X4 can drive and set load tag, set load here, that value. What DC will do now, it will know that okay, you are driving this much load, and it will always choose X4. The drive strength 4 of the register that is driving the output. So you are on the safe side. So now what do these constraints do? So the input constraint, input transition time, will let design compiler correctly calculate the delay of the logic here at the input boundary. An output load will enable design compiler to instantiate a higher drive cell here at this point. So you are safe on both the input side and the output side. I'll summarize again what all things you need to specify correctly the operating of the design environment. So this is a figure. So we saw how to set the operating condition. Operating condition sets the PVC of the design, the process voltage metric of the design. Always choose the worst case. We saw how to estimate the interconnect RNC values. We use set violode model. We use a violode model that is part of a library in most of the cases. Although there is something called custom violode model. So for a particular chip, your backend team or library team can come up with a custom violode model, which is specific to your chip. This is again a separate topic altogether, but there is one such case, so you can use that custom violode model. You use commands like set driving cell or set input transition. Don't worry about the set drive command. Set drive is not used extensively now. It's either set driving cell or set input transition at the input side. Although you could also set load at the input, but it will help again. So set driving cell and set load go together. You can set the driving cell and you can set the load. So that will help DC in calculating the transition time at the input. Or you could use set input transition directly. Again, at the output, you either set load, or you can also set fan out load if you know what kind of fan out is going to drive. Set fan out load. Set load is a capacitor number. Set fan out load is simply a number, that how many fan out will it drive. So in the next lecture, we'll look at the timing constraints, the clocks, input delays and output delays. Right? Thank you.